Big part of chapter 6 is factoring and solving. So this is factor completely. I'm actually going to take it one step further with you. And after we factor it, we're also going to solve, just so you can kind of make that connection to everything. So if you look at this problem, we have n to the fourth minus 1. This is a problem you could potentially look at as a quadratic sum. It's also a problem you could look at and hopefully would see a difference of squares. Because n to the fourth is a perfect square, and 1 is a perfect square. So when I see this, I see n squared minus 1, n squared plus 1. And then what you should do is notice that m squared minus 1 is a difference of squares again. So that becomes m minus 1, m plus 1, m squared plus 1. Remember, a sum of squares is not a formula. The reason I said, hey, let's solve that is so that you could see here, again, we had one sign change. So that one sign change meant one positive possible root. When you solve this, your positive root is 1. If you plugged in the negative m, then it stayed m to the fourth, and you saw that that also said we had one negative possible root. And again, it's m to the fourth, so if you can only have one positive and one negative, then that guaranteed that I had 2 imaginary. And if you solve this, you should see the positive, the negative, and the 2 imaginary. So that if you were to graph that m to the fourth minus 1, zero, 0. Leading coefficient is positive. Degree is 4. That means that n's high. And again, if it's a quartic, it has to have 3 extrema. So if it's a quartic, it has to have 3 extrema. We also know that the y-intercept was negative 1, and we knew my 2 zeros were at 1 and negative 1. So that's how I knew this little point kind of happened here. And then I knew I had to have my extrema within there. So again, when I say like we're putting every problem kind of together, that's where I'm getting at. Like I want us to be to a point where we're starting to see all of those connections. That these graphs and examples all make up bigger pictures. 64n cubed minus 125. 125 is a perfect cube. 64 is a perfect cube. N is a perfect cube. This is an example of a difference of cubes. So you're going to plug into your difference of cubes formula. So that says 4n minus 5. Square the first, so 4 squared is 16. Square the last. It's always positive here, and the second sign is always the opposite of the sign you started with. So a positive, and then you multiply your 2 cube roots together. So 4 times 5 is 1. again, looking at that, when we look at the original problem, I have one sign change that tells me one positive root. If I were to solve this, 4n minus 5 gives me that one positive root. If you put a negative in for n, you get negative 64n cubed, negative 125, which tells you that you have no negative real roots. So if I have one positive and no negative, then I am left with 2 imaginary. If you were to solve this quadratic, and I could, but 20 squared is going to give me 400 and 400 minus all those big numbers, like, I don't really want to do that in my head. My calculator's back there. But you would get 2 imaginary roots. So you would do the quadratic formula to get those 2 imaginary solutions. And again, you see that from that discard scroll. That's where that rule is super nice. Okay, solve them. So again, if I look at this, I can't solve without being set equal to 0. Take out my GCF. X squared equals 0 is what we call that repeated root. And I bring this one up because the zeros mess up discard scroll. Because 0 is not considered positive or negative. So when you look here, you get one sign change. That tells you the one positive, which is x equals 3. When you plug in the negative, you get no sign changes. So it tells you no negatives. It leaves the potential for 2 zeros or 2 imaginaries. Remember, it's possible, not guaranteed. So I say if you can take out a GCF, you want to take it out first and apply your discard rule to what's left behind, not to what's inside. So same with here. You take away the b, you have b squared minus 8b plus 16. One sign change on each term tells you 2 positive reals, and then your 0. If you graph a repeated root, it hits but does not cross. So if I were to graph that cubic, leading coefficient is positive, degree is odd, so it tells me it starts low and ends high. You could plug in a number into. So if you plugged in -1, you have -1 minus 8 minus 16. So you're way down here, right? We know 0 crosses. I don't know what happens here. Somewhere between 0 and 4, I have an extrema. And then it's going to go up. Up. Hit, but not cross. It's going to come up, hit, but not cross because it's a repeated root. You still have 2 extrema happening in there. making it a cubic. A max and a min. You still see your two extrema even with a cubic root. So again, you could say, all right, a rel max approximately, at 2.5, and a rel min is at 4. Your zeros are at 0 and 4. Just kind of like repeating terminology and giving you a better understanding. If a polynomial equation is degree n, then you can count multiple roots separately. If a plus bi is a root, then a minus bi is also a root. So again, if I were to give you 3 roots and one of them had a negative I in it, then you have to put the positive I. If one of them has a positive I in it, then you have to create the negative I. And that was the last page to like the homework on Friday. Our rule for signs says that the number of positive zeros is equal to the number of sign changes or is less than that number. And again, that's the idea. It's 2 or 0. It can be less than it. That number represents the maximum. If there is only one variation in sign, then there is exactly one positive real zero. The number of negative real zeros of f is either equal to or again less. So using that rule, determine the number of positive and negative real zeros. No sign changes, therefore no real zeros that are positive. No sign changes, no positive real zeros. Plugging in your negative. You get negative x cubed plus 2x squared minus 5x plus 4. Well, now I have 1, 2, 3 sign changes. So 3 sign changes tells me that I can have 3 or 1. I can't have 2 because of the way the imaginary have to come in pairs. So I can have 3 or 1 negative real zeros. And that means the imaginaries are 2 or 0. So if I have 1 negative, I have 2 imaginary. If I have 3 negative, I have no imaginary. To follow on to that, if I ask you to list the possible rationals, you better not put plus or minus. If I ask you to list the possible rationals, this is not a plus or minus because there are no positive. So your P divided Q would only be -1, -2, and -4. So if you were going to set up synthetic and try to find them, you were only using the negatives. So again, these are your possible rationals. Not guaranteed, possible. that's what the rational zero theorem says. It gives a list of possible rational zeros. Not everyone will be a zero, but if there is a rational zero, it will be in that list. So listing all of the possible are the factors of the last over the factors of the first. So you start with all your factors, but then the list needs to be concluded by actually taking the tops and dividing them. So it's plus or minus 1, 1/3, 1/5, 1/15, 2, 2/3, 2/5, and 2/15. Have to write them out as separate fractions if I ask you to list them. Putting the top number over the bottom number is not listing the rational zeros. So I'm looking for the bottoms. Then if it asks you to go further and to factor it and find those zeros, you would do your rule and set up synthetic. So the last example is solving that polynomial. So again, solving will be set equal to 0. We have a quartic. That means I have 4 potential zeros. If you look at your sign changes, I have 1, 2. So that means I have 2 or 0 positive. Plugging in a negative x, we have x to the 4th minus 6x squared plus 8x plus 24. So that gives 1, 2. So that means you could have 2 or 0 negative, which means I could have 4, 2, or 0 imaginary. The possible rationals would come from P divides Q. So that's 1, 2, 3, 4, 6, 8, 12, and 24. Looking at 1 like quickly, 1's not going to work. You have like 1 and 24, so that's 25, 25 minus 14 isn't going to work. So like I'm not going to bother with 1. Negative 1, again, you're going to give me 24 plus 1, 25 minus 6, which is 19, and then I'm going to have adding a number to that. So that's not going to help me. So when I'm trying to pick it, yes, I am plugging in kind of quickly, as well as like looking for it. So maybe I try 2, so on and so forth. I know I'm down to a minute, so I have the work for that. I can send you a picture of it, so you can go back and check it. The last page of the packet was like the beginning of the chapter stuff, but your test really isn't going to focus on. So I, kind of photocopy these reversely on purpose. I would post that answer page